All right, this video is for investigation number 2, which is part of the Unit 11 Graphs of Polynomials unit. All right, so you're going to need a graphing calculator for this investigation. So for each of these graphs, what you're going to do is you're going to sketch the graph on your graphing calculator and then make a rough sketch. Mostly we just want the x-intercepts plotted on the graph. And then we're going to look at the degree, the solutions, and then the behavior, what is happening at the x-intercepts. All right, so number 1 says the function f of x equals x minus 5. Before we even look at the graph, we should know that the degree of this polynomial, the highest exponent here, is 1. That's a linear function, and because the degree is 1, we have learned that the number of roots or solutions is equal to the degree. So there's going to be one solution or root for this linear function. Now, where is the x-intercept? Well, that's where the graph comes in. Now, for this line, we definitely do not need to use our calculator. So what we're going to do is we'll just graph it by hand, but we'll use the calculator for the rest. With that linear function, I know that the y-intercept here is at -5, and this graph has a slope of 1. So we can graph all the way up in both directions, and you will have a line. And you should be able to see that the x-intercept of that linear function happens at x equals 5. Now, the behavior is what's happening at that x-intercept. Well, it looks like that my graph is crossing through the x-axis at that x-intercept. So that is the behavior. It is crossing through. All right, number 1 done. Number 2. I have a function x minus 4 times x minus 4. Now, simplified form here is actually we're going to just condense that together. So if I have 2x minus 4s being multiplied, I can rewrite that as x minus 4, the quantity squared. Now, we do need to know the degree. And I'm going to show you a couple ways to find the degree. I'll show you the long way, and then I'll show you the shortcut of how we're going to find the degree. First way we normally find the degree is we need to know the standard form of this polynomial. So if I started with x minus 4 times x minus 4, I would go ahead and distribute in order to get standard form. So I get x squared minus 4x plus 16, which then the standard form would be x squared minus 8x plus 16. And from looking at standard form, we would know that our degree, the highest exponent here, is 2. Again, because my degree is 2, that means I'm going to have 2 roots or solutions. Now the faster way, because these are going to get more complicated and we're not going to want to distribute every problem. So in order to find the roots, or the number, in order to find the degree from this factored form right here, you just go ahead and count up the factors. I have 1 factor, 2 factors, which gives me a degree of 2. Right? Because when I multiply those x's together, x times x will give me x squared, which shows me the degree. This is a quadratic function, so I'm going to graph this so I can sketch my graph. All right, you can graph either the original or you can graph the simplified form. I'm going to graph here our simplified condensed form. And when I graph this, I should be able to see that it looks like I have an x-intercept here at x equals 4. So if I sketch this graph, I'm only worried about the x-intercept, so I come down. Oops, that wasn't very good. I come down, I bounce off, and that is the sketch of my parabola. Now we'll talk again in a second how we can do this without even using our calculator. But when I look at that graph, I have an x-intercept at x equals 4. That comes from this factor. My other solution is also at x equals 4. And at the x-axis, that graph is touching or bouncing off of the axis. Now, I used my calculator to sketch that graph. However, another way I could solve this if I had the factored form x minus 4 times x minus 4 is to use the zero product law. That says if I set each factor equal to 0 and solve each of those equations, I get my solutions. And notice, those are the same as the x-intercepts and solutions that we found. All right, so let's shorten this because we did a lot of work on this problem in order to get to our answer. So I have the next graph, number 3, x minus 1 times x plus 3 times x plus 3. Let's simplify that. Let's condense it. There's no other x minus 1, so I'll just write one of those. But there are 2 x plus 3, so I'll write the quantity squared. Now, in order to find the degree, let's just count up the x's. There's 1, 2, 3 of them, 3 factors. When I multiplied them out, will give me a degree of 3. That tells me I will have 3 solutions. Now, let's see if we can find the x-intercepts before we go to our graph. So if I were to use the zero product law, I would set each of these factors equal to 0. I would solve each equation, and I get a solution at x equals 1, x equals negative 3, and x equals negative 3. So those are my x-intercepts. So now let's take a second and graph the function so that I can see what it actually looks like here. So again, I'm going to graph my condensed form, but you can graph the original function if you would like. All right, so hit graph, and that's the graph we're going to sketch on our paper. So notice that x equals 3 looks like it bounces off, and it looks like it goes through at x equals 1. All right, so negative 3 here, and 1 are my roots. I come up, I bounced off, and I went right back through. We just want the shape of the graph, it doesn't have to be perfect. All right, so let's double check. At x equals 1 right here, I crossed through the axis, and at x equals negative 3, I touched or bounced off the x-axis. All right, a few more. Hopefully you're seeing how you're going to do these here. So let's look at number 4. I need to first simplify, condense this polynomial. I have 2x plus 2's, so I'll write x plus 2, the quantity squared, x minus 2 times x minus 3. Now the degree, again, I count up the x's. There's 1, 2, 3, and 4. This is a quartic degree 4 polynomial, and because the degree is 4, that means the number of solutions is also equal to 4. Now from that factored form, if I did the zero product law here, I'll do it on the last time here, and then on the next one, hopefully we'll have gotten the idea. You would technically take each one of these factors, set them equal to 0, and solve them for x. So the first one gives me a solution of negative 2. Again, if I subtracted 2, I get another solution of negative 2, positive 2, and positive 3. All right, now let's make a picture of our graph so we can see what actually happens at those roots. So I will graph here x plus 2, the quantity squared, times x minus 2, and x minus 3. When I graph, you can't see the top, but we can imagine that it goes up and comes back down. And that's the picture that you're going to sketch. So if you need to pause the video in order to sketch the graph, that is fine. All right, I have roots at negative 2, positive 2, and positive 3. So my graph looked like it came down, went off the graph, it comes back down, and then did something like that. It's not perfect, but I can see that's the general shape that was on my picture there. So what's happening at the root? What is the behavior? Well, at x equals negative 2, it looks like I'm touching or bouncing off the axis. At x equals 2, I'm crossing, and same at x equals 3. All right, let's look at 5. This one's going to have something a little bit different. So my simplified form here, I have x times x times x, which is x cubed, and then x plus 3, the quantity squared, because there are 2 x plus 3's. I count up my x's in order to find the degree. There's 1, 2, 3, 4, 5 of them. So this is a degree 5 polynomial. It's quintic. degree 5 polynomials have 5 solutions. The solutions is equal to the degree. Now, if I were to set each of these factors equal to 0 and use the zero products law, when I have a factor of x, and I set that equal to 0, well, that tells me I have one solution at 0. I have 3 of those x's, so 3 of my solutions happen at 0. At x plus 3, if I set that factor equal to 0, I solve it and get a solution of negative 3. There are 2 of those solutions. So we haven't had one with 3 yet. Let's graph and see what happens here. So it's x to the third times x plus 3 squared. Oh, that looks kind of cool. So the bouncing off part we've seen, it kind of squiggles through the origin at 0. So pause the video, make a sketch of this one, and I'll do the same. So I have negative 3 and 0. Looks like it came up, went back down, and then I actually kind of squiggled through the axis right there. So what happens? What's the behavior? Well, at 0, I definitely crossed through. So all 3 of those are going to be crossed through the axis at 0. At negative 3, I touch and bounce off the axis. One more graph and then we'll tie it all together. All right, we have to really simplify things here. There's no other x minus 2's. There are 2 x plus 3, so x plus 3 squared, and 3 x minus 1. When I count up the x's, there's 1, 2, 3, 4, 5, and 6. So this is a degree 6 polynomial, which means I'm going to have 6 solutions. Now let's graph it so we can see what's happening at those 3x intercepts. We know we'll have a root at 2. Oh, I'm sorry, I guess I should write this down. Using the zero product law, from x minus 2, that's going to give me a solution at positive 2. X plus 3 gives me 2 solutions at negative 3, and I'll have 3 solutions at positive 1. Right, so I'll have 2, 1, and negative 3 here are my roots. So let's take a look at what this graph does. Oops. Let's go back here. All right, x minus 2 times x plus 3 squared, and x minus 1 cubed. All right, so we have that same squiggly thing again. It comes off the top of the graph, but I can estimate what the picture looks like here. So it looks like I'm going to come down, bounce off, come back up, and then on this root here at 1, when I look at the picture, it looks like it squiggles through there. So I need to make sure when I come down, I squiggle, and then I go back up. Now I know it's not perfect because the graph goes off the axis, but you have the right idea here. All right, let's see what happens. At x equals 2, I cross through the axis. At negative 3, I touch and bounce off the axis. And then at 1, even though I squiggle, I cross through there. So what did we just discover? We just had a bunch of factor form and looked at graphs and talked about where things cross and don't cross. So what does that actually tell us about polynomials? Well, first of all, what's the relationship between the degree and the number of roots? Well, we learned this in the first lesson. They are equal. Right? When we had a degree of 6, we ended up with 6 solutions. Now, for example, when I looked here at 6, I had 6 total solutions, but were they all unique? Were they all different? Well, no. 2, negative 3, and 1 are only 3 different numbers, but I had 6 roots. Some of them repeated themselves. Same thing for all of these here. Looks like with degree 5, this problem, I had 2 unique roots. For degree 4, I had 3 unique roots. And degree 3 had 2. So as I look through this, while the number of roots is equal to the degree, there is no relationship between the degree and the number of unique or different roots. That means some of the roots are allowed to repeat. Now, in general, all the factors that have even multiplicities are the exponents, the number of times the multiple time that a root showed up. So for example, in this last problem, this x plus 3 had a multiplicity of 2 because there were 2 factors of x plus 3. X minus 1 had a multiplicity of 3 because there were 3 factors of x minus 1. So the question is, factors with even multiplicities will do something at the x-axis. Well, here when I had 2 as my multiplicity, that was the root of -3. Well, look, it touched the axis. If I flip back, I have a multiplicity of 2 for x plus 3. That's at -3 here. I touched the axis. Same thing, if I went through all of these and -2, I touched the axis. Okay, so it looks like if I have an even multiplicity, I will touch the x-axis. Or I like to say bounce off. Now factors with odd multiplicities, it means 1 or 3. So for example, here I had 3 at x equals 1. Those all seem to cross. Because here, x minus 2 had a multiplicity of 1, and it crossed over the x-axis. All right, so now, factors with a multiplicity of 1. So for example, x equals 2 on this first problem here. X equals 2 happens right over, I meant to highlight that. X equals 2 happens right there. That factor, that x-intercept, is going, I put the wrong thing, is going to look linear at the x-intercept. So what linear means is it's going to look like a linear function. It's going to cut right through without squiggling, without turning. It is going to go straight through the axis. Now factors with a multiplicity of 2, the ones that touch or bounce off the axis here, right, like this one, those are going to look quadratic at the x-axis. And a sketch of that would be that they just come down and touch and bounce back off like a parabola would. Now finally, this is the cool one, factors with a multiplicity of 3. Right? Well, 3 would be like this squiggly guy right here. Or this squiggly guy right here. Those actually look cubic at the x-axis. And a cubic function, like the parent graph here, squiggles through. So you need to know what is going to happen at the root depending on the multiplicity of that root. We're going to be sketching graphs, and I'll go through one of the practice here in just a second. Now let's count the multiplicities for each of the functions, right? So number 1. So we'll go way back to the beginning. The multiplicity, so if I were to put this in parentheses, there's only one of these factors. So the multiplicity for number 1 there is just 1. Let's go back to number 2. The multiplicity for graph 2, well, the only exponent here is 2. So the multiplicities on this graph is 2. And notice we're going to make a connection. The degree of this polynomial is 2. Okay, so the multiplicities here for graph 2 or 2, the degree was 2. Right, if I go back to graph 3, if I add up the multiplicities, 2 and 1, I get 3 total multiplicities, which was the degree of 3. Okay, so degree of 3. Multiplicities for 4, well, I have a 2, a 1 and a 1. 2 plus 1 plus 1 is 4. That's the degree. All right, I think you're seeing the pattern here. For number 5, we have a 3 and a 2. That adds to 5, degree of 5. And for the last problem, we have a 1. a 2, and a 3, that's 6. Degree of 6. So, the big thing to know here is that the sum, adding up all of the multiplicities of every root in a polynomial, is equal to the degree of the function. All right, so that's your investigation. Let's do a problem together, like number 1 here on the practice, just so you get an idea of what the practice needs to look like. All right, so what we have says without your graphing calculator, find the degree, the number of roots, and the multiplicity of each root. We'll then talk about the end behavior, we'll sketch a graph, and so forth. Okay, we will do a lot of practice on this over the next couple of days. So first thing, the degree of this polynomial. Well, remember, we just said the degree of a polynomial is equal to the sum of all of the multiplicities. So when I look here at the multiplicities, I have a 2 and a 1. 2 plus 1 is 3. So this graph has a degree of 3, which it doesn't ask you, but that's called a cubic equation. Degree 3 means that you're going to have 3 total roots, real or imaginary, but 3 total roots. And when I have 3 roots, remember the maximum number of times this graph can change direction is 2. 1 less than the degree. Now I'm going to come back into the end behavior in just a second, but let's talk about the roots here. Remember, we use the zero product law. This root of x minus 5, well, it actually gives me a root at positive 5. Now, its multiplicity is 2. That's the exponent on that root. So its multiplicity is 2, which means it's an even number. It's going to touch or bounce off the axis. And we said even multiplicities of 2 are going to look quadratic at the axis. So it's going to bounce off. The other root here is that x equals negative 2. Well, its multiplicity, there's only one of those. That's an odd number. The odd multiplicity means you're going to cross through the axis at negative 2. And multiplicity of 1 means you're going to look linear. All right, so let's make a rough sketch. Draw an axis. And I would plot your x-intercepts. So my x-intercepts are negative 2 and 5. Okay. Now, I have a degree 3, so it's odd degree. Odd degree means that my arrows are going to point in opposite directions. And when I look here, my leading coefficient of this polynomial is positive. So my graph is overall going to have a positive trend. It's going to start low and end high. So if I have a positive trend, my graph needs to start down here and end up here somewhere. All right, now at x equals negative 2, my graph's going to come through. It's going to cross through and look linear at that root. So I'm going to come up through. Now I need to turn at some point because I need to come through 5. So I'm going to come up. I need to come down, but at 5, remember, I'm going to look quadratic. I'm going to touch the axis. So I'm going to come back down and bounce off the axis to end going in that positive direction. If you're not sure, go ahead and sketch the graph here. You can sketch x minus 5 to the second times x plus 2. That's what our graph looks like. It's hard to see, but you know it comes back down. You won't have your graph on the or your calculator on this quiz, but you can at least sketch to practice here. Finally, end behavior. As x goes to the left, negative infinity, my arrow, my y values are going to negative infinity. As y goes to positive infinity, as x goes to positive infinity, the y's are going to positive infinity. All right, try the rest of the practice, and go ahead and ask your teacher for help if you have any other questions.